Hello and welcome back to Differential Equations, section 7.3 on translation and partial fractions, which we mostly done in the past. So we will be focusing on translations here mainly. We'll do some partial fractions, obviously. This is a quick section, and then we will jump into 7.4 to do as much as we can. Next week we are going to do 8.1 and 8.2, and then have the course review, and then another review following Monday for those of you that will be taking the final in the Monday afternoon, if you're, or whatever, exam 4. You will be taking one or the other. We talked about it. All right, so let's take a look at translations and partial fractions. So we start with just all of the definitions for partial fraction setup, just in case. Again, you're supposed to know all of this from Calc 2 because that's where the section is, but then, you know. So partial fractions setups. So you can have, usually I write blah, something over x minus c. The setup is a over x minus c. Then blah, x minus c squared. That's going to be a x minus c plus b over x minus c squared. Then we have irreducible quadratic. So you can't factor this one, right? If you can factor it, then you would get two linears, and then you can use, right, the first or the second one. But since this one is irreducible quadratic, that's going to be ax plus b divided by ax squared plus bx plus c. And finally, repeated irreducible quadratic, which would give us this. And as you can see there, it follows the same recipe like the repeated linear, right? So you repeat the same numerator with different constants, obviously, and then the denominator, oops, there's supposed to be a square there. All right, so this is what you're supposed to know from Calc 2. And when you get a couple of these values, right, terms, then you factors. There is a charm. When you have a couple of factors in the denominator, you're supposed to set up partial fraction decomposition, calculate all of the constants, and then do the inverse Laplace. So that will be our partial fractions. And now we have our translation. On the x-axis, translation means move, right? So if f of s is the Laplace transform of f of t, right, exists for s larger than c, then Laplace transform of e times a to the t times f of t exists for s larger than a plus c, and Laplace transform of e to the a t times f of t is equal to f of s minus a. Also, we have the inverse Laplace of f of s minus a is equal to e to the at times f of t. This over here is a translation on the x-axis, and it literally means move it right or left a units. So if you want to move something 3 units to the right, you just subtract 3 if you as a. So you will multiply the original function by e to the 3t, or negative 3t. Which one did I say, left or right? I don't know, whatever I said. So this is just a quality of life kind of deal, because what it does is it shifts and allows us to it shifts, I mean, in application, but it allows us to do less calculations, right, and less partial fractions and all of that stuff, because, right, we are memorizing formula over here which skips the calculation. Right, you memorize the product rule for derivatives, you memorized partial fraction decomposition, you memorized the integration by parts, right? So memorizing this formula as well, it's you know, one of those deals. Now let's take a look. Something cool. So I'm looking at these examples in a textbook, and we'll definitely need to go to example 1. Example 2 is completely unnecessary because we already did a couple of those problems. Example 3 unnecessary as well. Yes. Example 4 is this one converted, easy, also not a problem. So looks like we just need to look at the translation. Yeah, all right. So example 1 on translation. The rest is just basic partial fraction decomposition, which we did last class. I don't want to spend too much time on this lecture because the lesson focuses like 80-90% on partial fraction decomposition, which we did last time. All right, so here is the problem that we need to carefully look at. It says 1/2 x double prime plus 3x prime plus 17x equals to 0, with x of 0 equals to 3 and x prime of 0 equals to 1. Remember, when you are dealing with Laplace transforms, you absolutely must have these, otherwise it's not going to work at all, right? You have those terms worked into the Laplace of the derivative. So if you don't have these, right, you can't solve the problem. All right, so let's go. The first order of business over here is kill the fraction by multiplying all of this by 2. So that gives us 2x double prime plus 6x prime plus 34x equals to 0. That makes everything easy. And then we are supposed to hit this with the Laplace, right, to transform all of this. So this is going to be 2 times. And now over here we have our s squared f of s. We can also use x. X of s minus s x of 0 minus x prime of 0 plus 6 times s x of s minus x of 0, and then plus 34 f of s equal to 0. So shouldn't just say, oh, I multiplied by, yes, sorry. Yes, you're right. When I multiply everything by 2, it gives me, yeah, it cancels the half. Yeah, I was testing you. Very good, Aldana. Yes, very good. I was testing everyone, making sure that you are paying attention, and you are definitely paying attention. That's very nice. S squared x of s minus, oops, s x of 0 is 3 minus 1, and what else do we have? Plus 6s x of s minus 6x0 is 3, and then plus 34 f of s equal to 0. And now we get all of this together, or all of the, why do I'm mixing f's and x's. 34 x of s, x of s, there we go, better. I'm used to f, and then we kick in with x, and just, so factor out x of s, and we get what in parentheses? We get s squared plus 6s plus 34, and then we have minus 3s, right? Minus 3s, and then I have negative 1, and negative 18 is negative 19, equal to 0. So when I solve this for x of s, I get 3s plus 19 when these two go to the other side, and then divided by s squared plus 6s plus 34. So I hope that's our 3s plus 19, s squared plus, okay, good. So now we are going to try and factor this, right? So that's what you try first. And if factoring doesn't work, then you have to do completing the square, because then you will get translation. So try factoring first. And if factoring doesn't work, then you will have to go and do completing the square. So we have to do 34. That's the ugliest 3 I ever written in my life. There we go. Now it's the ugliest 4 I've ever written in my life. I give up. So I have 1 and 34, 2 and 17, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, these are it. And we can't make 6. So can't make 6, can't factor, right? So in this case, cannot factor. Always put a little sad face there. So we use completing the square. Now that's your intermediate algebra, where you complete the square by taking 6, cutting it in half, squaring, you get your 3 squared, which is 9, which is the magic number we add and subtract to the mix. So this becomes s squared plus 6x, and then this is where you put your plus 9 minus 9, and then you have your plus 34. Now some of you are already advanced in these techniques, so you know that you just, instead of writing plus 9 minus 9, you steal 9 from 34, leaves the 25 behind, because this will combine into 25 anyway. But again, that depends on how advanced you are in doing the completing the square. It's important to do it and to have it right. Now, you know which way you did it, don't care. First 3 are completed square, which is square root of the first, sine of the second, square root of the third. and then you have plus 25 at the end, and that becomes your denominator. So what you have is 3s plus 19 divided by s plus 3 squared plus, and I'll put 5 squared because I am a boss. So now when I split this into into two fractions, I get 3s over s plus 3 squared plus 5 squared plus 19 over s plus 3 squared plus 5 squared. And you know that one with the s works out to be cosine, one with the number on front works out to be sine. You just have to be careful with those coefficients, right? So so those are the forms. Now we also have, and this is the new creature for translation, this guy. So for your sine and cosine, right, for the transform, you used to have your cosine kt was transformed into the s over s squared plus k squared, right? So there was just s over here. Now I have s plus 3, right? So if I have s plus 3, then that's multiplied, right? The AAT cosine KT gives us s over s minus a squared plus k squared. So, and I believe this is the part of your chart in the front. Let me just verify. Yes, it is. Line number 1, 2, 3, 4, 5, 6. Line number 7 on the right hand side of the chart gives you this formula. Now, this doesn't work only for trig, it works for everything, right? They singled out the trig formulas there, but it works also for hyperbolics, for technically all the transformations you have, if you just need to move it 3 units. So what I learned over here is that my a is technically -3. That's what I have for these problems. So when you are taking a look at this xs, this is going to be 3 times s over s plus 3 squared plus 5 squared. So I move these 3 because, as you can see in the cosine formula, all I need is an s there. Plus, I'm going to move 19 out, divided by, I'll leave that open for now. And then I have this one is my s plus 3 squared plus 5 squared. You see, I need a 5 here because I need, for sine kt, I need k over s squared plus k squared, right? So my k is 5, so I have to have 5 up there, which is why I left this spot on the bottom to fill in the counter 5 that we need for it. All right, so now this a equals -3 will spit out e to the -3t multiplier for the whole inverse, and I will have, right over here, when I now go in here and I apply inverse Laplace, this becomes x of t, because inverse Laplace takes the x of s into x of t. And I will have, so this term will say, because it's s plus, it's not s squared, it's s plus 3 squared, it spits out -3 to the t. And then we have times 3 cosine 5t. And then we have plus, this guy spits out e to the -3t, and we have our 19 over 5 sine 5t. Now I have xt is equal to e to the negative 3t, and then 3 cosine 5t plus 19 over 5 sine 5t as a solution. Now, if you are to go back to the original problem and solve it using r squared plus 6r plus 34 equal to 0, you will get the same answer. You have to, right? It's just this one is done using Laplace. Again, we are using a sledgehammer on a problem that is, you know, basic nail into the wall for the little picture frame. But when the problems get more complicated and annoying and the other methods don't work, right, this method is the one that would be used. So, I mean, today you use computer to solve all of this stuff. You don't do anything by hand. But, you know, hypothetically speaking, let's say you're somewhere you don't want to be and someone asks you how are you, and it was beautiful weather and so on, you immediately answer with this stuff. At least that's what I do. As soon as someone starts talking about how nice weather it is, you know, people meet at the elevator. Beautiful day today. Yep. And the inverse Laplace transform off, and you don't have to deal with them ever again in life, which is always a plus. All right. I would say that's it for this lecture, unless I can really snipe another problem. That we can do quickly. Now let's take a look at one more of these puppies. Yeah, problem number 8 real quick and then be done. So f of s is given as s plus 2 divided by s squared plus 4s plus 5. Oh, by the way, where do these problems appear? Anytime you have a dash pot, right? Because, guys, you are getting this term here in your answer. This is the term that kills the oscillation, that makes the object stop. So if you have the gravity, you have the air resistance, you have the dash pot, right? All of the things in your mechanical systems for pendulum and so on, right? That would actually make the system stop. That's where these types of translation, right, problems would kick in. Looking at the problem that we are converting over here, if that was a negative, it would be factor, and then you use basic partial fraction decomposition. But because it is not negative, it's positive, we have to do completing the square. So half of 4 is 2, 2 squared is 4, so still 4 out of 5. So I have s squared plus 4s plus 4 plus 1. The first 3 will give me s plus 2 squared, and then we have plus 1. And you can put 1 squared if you want to. So now my f of s is equal to s divided by s plus 2 squared plus 1, you can put a square there, plus 2 times s plus 2 squared plus 1 squared. The first one is already set up for us. The second one, I'm going to drop the 2 in front and leave the 1 on top because our k is 1 and we need k over, right? And we also know that a is equal to negative 2, right? Because it's s plus 2. The definition is s minus a. So if you have s plus 2, then minus a is equal to 2a is negative 2, if you want to think about it a little bit. So when I hit this with the inverse Laplace, we are going to get the f of t is equal to e to the negative 2t cosine t plus 2e to the negative 2t sine t. Your k is 1 in both of these, so it's just k times t is 1 times t. Factor out e, and then you get your f of t is e to the negative 2t. In parentheses, you have a cosine t plus 2 sine t. Now, if you want to flex and things, you can combine this into a single cosine function with that phase shift, and that depends on how much you want to flex in mathematics. Or if the person in the elevator had a follow-up question right after, or statement after the weather was great, something like, oh boy, it's gonna be busy at the store today. Yeah, hit them with the follow-up Laplace then. So that would be it for 7.3. As I said, very short. We only did translation. Partial fraction decomposition stays the same as Calc 2 and stays the same as our last class. I'm going to restart the stream. We'll be back in less than 5. I'm gonna go get the bottle of water as well. 7.4, derivatives, integrals, and products of transforms. This is going to have convolution and some other interesting stuff. So that will be it. See you in less than 5.